The biggest problem with cars today isn't electric versus gasoline. It's something much deeper. Every car, gas, hybrid, even most advanced systems, is built around the same 100-year-old mistake, forcing an engine to directly drive the wheels. And that decision quietly created one of the most inefficient energy systems ever mass-produced. Because an engine doesn't want to behave like that. It doesn't want to constantly speed up, slow down, react to your foot, or match the chaotic demands of the road. It wants to run in one perfect condition. And everything else, the gearbox, the gears, the complexity, exists just to fight against that reality. But there was a different idea, an architecture that didn't try to control the engine, but freed it from the car entirely. No mechanical connection, no compromise, just pure energy conversion. It worked, and the industry walked away from it. For most of automotive history, the way a car moves has barely changed. Fuel is burned inside an engine. That engine spins a crankshaft, and somehow, that spinning motion has to be translated into movement at the wheels. Simple in theory, brutally complicated in reality. Because an internal combustion engine doesn't produce power in a smooth, usable way. It behaves more like a narrow band machine. At low speeds, it struggles to generate meaningful torque. At high speeds, it becomes inefficient, noisy, and mechanically stressed. And somewhere in between, there's a small window where it actually works well. That window is where the engine is efficient, where fuel consumption drops, where performance feels right. The problem? A car doesn't operate in a narrow window. It lives in constant chaos. Stop-and-go traffic, highway cruising, sudden acceleration, climbing hills, descending slopes. The demand on the wheels is always changing, but the engine doesn't want to change with it. And this is where one of the most important inventions in automotive history comes in. The gearbox. At first glance, it looks like a solution. Multiple gears allow the engine to stay within its usable range while still adapting to different driving conditions. Low gears for torque, high gears for efficiency. But underneath that elegant idea lies something else entirely. The gearbox is not solving the problem, it's managing it. It's a mechanical workaround for a deeper limitation. The fact that the engine itself is fundamentally mismatched to the job of directly driving the wheels. And over time, that workaround became more and more complex. Manual transmissions evolved into automatics. Automatics became dual-clutch systems. Then came continuously variable transmissions, machines designed to eliminate fixed gears entirely, chasing an impossible ideal. Keeping the engine exactly where it wants to be, while the car does something completely different. This is where the story becomes interesting, because by the early 20th century, engineers had already realized something uncomfortable. If the engine only works efficiently in a narrow range, why are we forcing it to follow the wheels at all? Why not let the engine do what it does best, run at a constant optimal speed, and separate it completely from the act of driving? That idea didn't come from modern electric vehicles. It didn't come from Silicon Valley. It came from a much older concept, one that the industry explored, understood, and then quietly left behind. At its core, the problem isn't the engine itself, it's how we force it to behave. An internal combustion engine is, fundamentally, a thermodynamic machine. It converts chemical energy from fuel into mechanical work through combustion. But that conversion is incredibly inefficient. In most real-world conditions, a typical gasoline engine only converts about 20 to 30% of fuel energy into useful motion. The rest, lost as heat, through the exhaust, through cooling systems, through friction. But even that number is misleading. because that 20 to 30% only happens under very specific conditions, a narrow band of RPM and load where the engine is optimized to operate. Move outside that window, and efficiency collapses. And here's the critical part. Driving a car almost never allows the engine to stay in that window. Every time you accelerate, the engine is pushed into inefficient zones. Every time you brake, energy that was just created is thrown away as heat. Every time you cruise at slightly the wrong speed, the engine is operating in a suboptimal state, which means most of the time, the engine is not just inefficient, it's operating exactly where it was never meant to. And this is where the drivetrain makes things worse. Because once power leaves the engine, it has to pass through a chain of mechanical components before it reaches the wheels. The clutch, the gearbox, the drive shaft, the differential. Each step introduces loss, friction, heat, energy dissipation. Individually, these losses seem small, but together, they compound. By the time energy reaches the wheels, a significant portion of it is already gone. And yet, despite all of this, the system has one more hidden flaw. It's reactive. The entire drivetrain is constantly trying to catch up with the driver's input. You press the accelerator. The engine revs up. The gearbox shifts. Torque builds. Power flows. But none of it is instantaneous. It's a cascade of mechanical reactions, and that delay forces the system to operate even further away from its optimal state, which leads to more inefficiency, more complexity, more compensation. This is the paradox at the heart of modern cars. We designed an engine that works best in stable, controlled conditions, and then forced it into one of the most unstable, unpredictable environments imaginable. The road. So we added gears, then more gears, then smarter transmissions. But no matter how advanced the system becomes, it's still solving the same fundamental mismatch. The engine wants stability, the wheels demand chaos, and mechanical systems are stuck in between, trying to reconcile two completely different worlds. This is where everything begins to break down, because once you see the system this way, you start to realize something uncomfortable. Maybe the problem was never about improving the engine. Maybe the problem is that the engine was connected to the wheels in the first place. There is another way to build a car, one that doesn't try to fix the engine, but removes it from the problem entirely. Instead of forcing the engine to respond to the wheels, this architecture breaks the connection completely. No drive shaft, no gearbox, no mechanical link at all. The engine no longer drives the car. It generates electricity. This is known as a series hybrid system, and on paper, it looks almost too simple. The engine runs at a constant speed, right in its most efficient range. It spins a generator. That generator produces electricity, and that electricity powers an electric motor, the only component connected to the wheels. For the first time, the engine is no longer reacting to the chaos of driving. It's isolated, stabilized, optimized, and everything that actually moves the car is handled by the electric motor. This changes everything, because electric motors behave very differently from combustion engines. They produce maximum torque instantly. They don't need multiple gears. They don't care about RPM in the same way. They are perfectly suited to handle the unpredictable demands of the road, stop-and-go traffic, sudden acceleration, precise control. All of it happens naturally. Meanwhile, the engine is doing something it was always meant to do: run efficiently at a steady state, without interruption. This is where the architecture becomes almost elegant. Instead of one system trying to do everything poorly, the workload is divided. The engine handles energy generation. The motor handles motion. Each component operates in its ideal environment. And when you look at the energy flow, something interesting happens. In a traditional car, energy is constantly being wasted through braking, through inefficiencies, through mismatched operation. But in a series hybrid, energy becomes something you can manage. Store it, buffer it, deploy it when needed. A small battery sits between the generator and the motor, not large enough to power the car for long distances, but enough to smooth out the system. It captures energy during braking. It provides bursts of power during acceleration. It stabilizes the entire energy flow. The result is a system that feels strangely modern, even though the idea itself is not new. In fact, versions of this architecture have existed for decades. Early experiments appeared long before modern electric vehicles. Later, cars like the Nissan e-Power and the BMW i3 with range extender quietly brought it back. And in every case, the underlying principle remained the same. The engine doesn't drive the wheels. It was never supposed to. At first glance, it might seem like the industry already found the answer. Electric vehicles, no engines, no gearboxes, no mechanical complexity, just batteries and motors. And in many ways, EVs do solve the fundamental mismatch. They remove the engine entirely. But in doing so, they introduce a different problem: energy storage. Because while electric motors are efficient, batteries are heavy, expensive, and slow to recharge, which forces EVs into a trade-off: range, weight, cost. Push one, and the others push back. This is where the series hybrid becomes uncomfortable to ignore, because it sits directly between two worlds. It keeps the simplicity and responsiveness of an electric drivetrain. Instant torque, smooth power delivery, no gearbox, but avoids the biggest limitation of EVs. The battery doesn't need to be massive. It doesn't need to store hundreds of kilometers of range, because the engine is always there, quietly generating energy in the background. In theory, this creates a system that is lighter, more flexible, and potentially more efficient in real-world conditions. So why didn't the industry choose this path? Why did most manufacturers move toward parallel hybrids or fully electric platforms instead of doubling down on this architecture? Because the answer was never purely technical. It was strategic. And this is where the story shifts from engineering to industry decisions. For over a century, the automobile has evolved through refinement. Better engines, smarter gearboxes, more advanced control systems, each generation improving on the last. But always within the same fundamental idea: the engine must drive the wheels. And for a long time that idea made sense, until the limitations became too obvious to ignore. So the industry began searching for alternatives. Some chose to remove the engine entirely. Others tried to combine old systems with new ones. But somewhere along the way, a different path briefly appeared. One that didn't try to fix the engine and didn't try to replace it either. It simply gave it a different role, not as the heart of motion, but as a source of energy. And then, for reasons that had less to do with physics and more to do with timing, cost, and strategy, that idea was set aside. But today, as the industry struggles to balance efficiency, cost, and practicality, the question is starting to resurface. Not loudly, not everywhere, but persistently. What if the future of the car was something we already understood? And what if the real mistake was walking away from it too soon?